Hello. Today we begin a discussion of Einstein's special theory of relativity. This is chapter 28. On the special theory of relativity. This chapter is one of three or four topics that collectively are described as modern physics. And so they include the special theory of relativity, the quantum theory, and a simple model of the atom. Quantum mechanics, and nuclear physics. So it is possible that we may have time to do all four of these. It's also possible that we may not. But these constitute modern physics. And these topics have been very well studied since the early 1900s. So we could say that they've been known for about 100 years. The physics that we have done up to this point, including mechanics, heat and thermodynamics, optics, this is typically described as classical physics. And so on. And this physics has actually been around for well over 200 years. And it has had spectacular results to the point that in the late 1800s, scientists had begun to believe that everything that was there to be known was known. And there remained a few minor problems, but they were very confident that they could iron out these problems using the physics that was known at the time. Unfortunately, that was not to be the case. There were two major problems that could not be resolved on the basis of the physics that was known then. And one of them, this is what I'm going to begin the lecture with, led to the theory of special relativity, and the other led to the development of the quantum theory and quantum mechanics. And these theories have done very well. Our knowledge today allows us to describe nature more accurately. So I'm going to begin by describing the problem that Einstein had to resolve. But in resolving this problem, Einstein forces us to rethink our very notions of space and time. Space as in the distance between two places. Here's an example. Everybody knows that the distance, let's say the distance or space, distance from, let's give an example, Tallahassee to Jacksonville. That's about 160 miles. And everybody is confident in their knowledge of what it means to say the distance from Tallahassee to Jacksonville is 160 miles. You can actually see the roads, right? You can measure the roads, the distances along the roads. And our concept of time, the journey from Tallahassee to Jacksonville takes about 2 hours. Time we shall measure with a clock or a watch. And these are two very different things, according to what we know. Einstein is now forcing us to rethink these ideas such that now we shall see space and time as not two very independent entities, but in fact two kinds of the same space-time continuum. Okay? So we shall see more of this as we go along. And here's another thing that Einstein's ideas introduced to us. The concept of mass, up to this point, we have held very different from the concept of energy. Kinetic energy, you know how to calculate kinetic energy. You calculate it from the mass. But Einstein's ideas force us to think of mass and energy as though they were equivalent. And we shall visit these ideas in a minute. But for now, let me describe the problem that Einstein had to help resolve, which is the following. Suppose that you take a battery, a power supply, and connect it to a heating element. Then by a process called thermionic emission, as in you heat an element and it emits electrons, you can generate a cloud of electrons that just sit there. They have nowhere to go, right? They just sit there. But if you now apply a very large potential difference, so you apply a very high voltage power supply such that this end here is positive, and let's say you put a little hole inside a disk here, then of course the high voltage accelerates these electrons and they pass through the hole, and so you can very easily measure the speed of the electron. To describe the speed of these electrons, we can use the physics that we know, which is to say that we can call this point here 1 and this point here 2, and use a conservation of energy and say the total energy at point 1 is the same as the total energy at point 2. And this comes from the conservation of energy. Well, at this point here, the electrons have absolutely no kinetic energy. Very small compared to the overall kinetic energy that they'll acquire once they have gone across this electric field. At this point here, they have no electric potential energy, so that our equation becomes E2 is all kinetic, E1 is all potential. So we could say that 1/2 mv squared is the same as the charge of the electron times the potential V. And so we can solve this for the speed as follows. So V becomes 2eV divided by m, and you take the square root of that. Well, it's a pretty straightforward calculation, right? And so we can also write this as 2e over m times the square root of the potential. Let's do an example. When the potential V is, say, 2.5 10 to the 5th volts, we can plug in these numbers. And you would obtain some values. We know the charge on the electron is 1.602 10 to the negative 19. The mass of the electron is 9.11 10 to the negative 31 kilograms. So you put in these numbers, and when you do the calculation, let's say 1.6 10 to the negative 19 divided by the mass of the electron is 9.11 10 to the negative 31. And then we shall multiply this by the square root of 2.5 10 to the 5th. When you do these calculations, you will end up with about 2.7 10 to the 8 meters per second. That's the speed of the electron. This, given that the speed of light is 3.0 10 to the 8, this is 90% of the speed of light. So we can write this as 0.9 times the speed of light. No problem. But look here. Our equation says that the speed of the electron is dependent on the square root of the potential V, which means that if we were to increase the potential by a factor of 4, then the speed should increase by a factor of 2. Okay, so when the potential increases by 4, so when we go from V to 4 times V, uppercase V please, the speed V should go to 2V, or 2 times 0.9 times the speed of light gives us 1.8 times the speed of light. So the prediction of this simple mathematics says that the speed of the electron should be 1.8 times the speed of light. Except that this is totally incorrect. If you increase the voltage across here, and you can keep increasing the voltage simply by adding more and more power supplies, no matter how much you increase the potential, maybe the speed of the electron will go from 0.9 times the speed of light to maybe 0.99 C to 0.999 C. You can increase it as much as you want, but you will never get to the speed of light. The speed of the electron can never become equal to 1 times the speed of light, let alone increase it past the speed of light as predicted here. It's not possible. Nature doesn't work that way. When scientists have repeatedly done this experiment, it is impossible to get the electron to go at the speed of light. So there is a problem. There's a problem with our physics. And we ask ourselves, what have we done wrong? Is it the conservation of energy, the law of conservation of energy, that is incorrect? Well, we know that the law of conservation of energy works in many, many instances. Is it our calculation of the kinetic energy using the formula 1/2 mv squared? Well, if 1/2 mv squared is incorrect, then Newton's laws are incorrect as well, or at least incomplete, because 1/2 mv squared, you recall in College Physics 1, we obtained from Newton's laws. So here is the problem. There is a problem. The physics that was known at this time could not explain why it was impossible to get the electron to travel at the speed of light. And this is where Einstein stepped in. So in describing, before we describe the theory that Einstein proposed, we need to be familiar with the language of special relativity. So I'm going to begin as follows. We shall first define the frame of reference. The frame of reference. The frame of reference you could easily define as the vantage point from which an observer measures distances and time intervals. That's good enough. So let's write it. So the frame of reference is the vantage point from which an observer measures distances or lengths and time. It's quite as simple as that. And typically we would use the X, Y, Z coordinate system to describe our experiment. Or for our purposes, we might just stick with one coordinate and just use the x-axis. And so we can just describe the experiment pretty well. Okay. Number two, let's define or redefine, restate the law of inertia, because we know it already, the law of inertia. You recall College Physics 1, Newton's first law of motion. An object will remain in its current state of motion at a constant velocity, meaning constant speed in a given direction, until or unless a force is applied to the object. That's Newton's first law of motion. But because it describes the tendency of the object to remain in its current state of motion, i.e., its inertia, Newton's first law of motion is also called the law of inertia. So, an object will remain in motion with a constant velocity. This is what you would describe as uniform motion. So unless a force is applied to it. Now let me point out that the first law is a special case of Newton's second law. Because Newton's second law states, you remember, that the net force, or the sum of forces that act on an object, is given simply by multiplying the mass of the object by its acceleration. Well, so clearly when there's no net force, i.e. when the net force is zero, then from here the acceleration is zero as well. And to say that the acceleration is zero means that the object will remain in its current state of motion, motion with a constant speed and a straight line. 3. We shall now combine these two, the frame of reference and the law of inertia, to define an inertial frame. And simply say the following: an inertial frame of reference is any frame of reference in which the law of inertia is valid. And if the law of inertia is valid, then Newton's second law must be valid as well. So an inertial frame of reference is any frame of reference in which the law of inertia is valid. Any reference frame that is in uniform motion is an inertial frame of reference. Uniform motion meaning, once again, constant speed in the same direction. So any frame of reference that is in uniform motion is an inertial frame of reference. And I mentioned this just to make the point that there are certain frames of reference that are accelerated. If the frame of reference is accelerated, then it does not fall within this description at all. If a frame of reference is accelerated, then that is a non-inertial frame of reference. So this is just by the side. So an accelerated is a non-inertial frame of reference. And about 10 years after Einstein had formulated the special theory deals essentially with how measurements performed in one inertial frame of reference transform into a different frame of reference, into a different inertial frame of reference. 10 years after that, Einstein formulated a more general theory of relativity, which dealt with accelerated frames of reference, and thereby gave us some new ways of looking at the force of gravity, universal gravitation. Okay, so the accelerated frame of reference is a non-inertial frame of reference, and this leads to the theory of gravity. Okay, but just pay attention. For everything that we shall do in this chapter, we will focus only on inertial frames of reference. Let's make a general comment on Newtonian relativity or Galilean relativity. Since, after all, Newton was essentially expanding on Galileo's ideas. Consider the following. Suppose that I have let's say one of you, okay, is an observer sitting on a train, in a train car that is moving at some speed, v. We can give it any, let's say it's 20 meters per second, okay? And here's one of you that sits here and has a ball in their hand and throws the ball up. So the ball goes up and comes back. Now, you know this from your own experience. If you are a passenger in a car that's moving, as long as the car is not accelerating, moving at a constant speed, you throw a ball up, the ball comes right back into your hands. So when you're seated, you're describing everything that is happening from your vantage point. And if you're holding on to the ball, you say, well, the ball has 0 speed from your vantage point with respect to your frame of reference. If you throw the ball comes right back down to you. Well, if you're trying to describe the mechanics of the ball, no problem. You remember the kinematic equations from college physics 1. So you would simply write y minus y naught equals v naught t plus 1/2 a t squared, and then this equation a takes on either plus or minus 9.8 meters per second squared, depending on your choice of the axis. But what if another observer were standing here on the embankment and is watching your ball? Since your ball is thrown while the train car moves forward, this observer sees the ball go from here to here. So from the perspective of this observer here, the ball travels like a projectile. Once again, no problem. This observer knows the equations that describe projectile motion, and then it's very similar to what you did up here. You just simply write this equation, but then you'll also write the fact that in the x direction, the speed of the ball is a constant. And if you combine these two, you can very well describe the projectile motion of the ball. So the point here is that none of these observers is doing anything special. There's no preferred inertial frame of reference to use to describe the simple experiment in mechanics. Both of these obtain very good descriptions of the motion of the ball. So we shall simply conclude from this that this inertial frame and that inertial frame are both equivalent for the description of the laws of mechanics. So we can generalize this and say that all inertial frames of reference are valid for describing the laws of physics. Let me actually make it more narrow here for describing the laws of mechanics. And this statement here is called Newton's principle of relativity. So in other words, no inertial reference frame is superior or special. And that all other inertial frames of reference can in fact be used to describe the physics of the ball. That's a contradiction though, and I'll point this out now. And let's use the following thought experiment. We do this very often in special relativity. We do a lot of thought experiments, okay? So imagine that, once again, one of you is in a train car that's moving forward. Let's increase the speed. Let's say it's moving at 100 meters per second. Let's say that this observer here has a ball that they throw forward. And let's say they throw the ball forward at a speed of 5 meters per second, let's say. 5 meters per second. So they throw the ball forward. There's an observer that's standing here. How does this observer describe the motion of this ball? Well, since the train car is moving at a speed of 100 meters per second and this ball is thrown at 5 meters per second, this observer will correctly say that the ball's speed is 105, and they obtain this by just simply adding 5 to 100. Well, before we move on, let's describe these with some variables. So this 5 meters per second here, this is the speed of the ball with respect to the train car. This is the speed of the train car with respect to ground. This observer here is measuring the speed of the ball with respect to the ground. And so he simply says this is VBC plus VCG. And we have a way of adding up our velocities in the Newtonian theory. No problem. So let's draw a little diagram. So if this is 5 meters per second, and all we do is that we just add our 100 meters per second to obtain the total speed of 105. So this is 5 and this is 100. But now let's say something different happened. Let's say that the train car actually had a light source here and suddenly turned on its light, so that the speed of light, the speed of light with respect to the car. What will this guy observe? This observer here, what will they observe? Well, we have a way of adding up our velocities. So let's quickly write this down. So according to this theory then, the speed of light with respect to the ground will be the same as the speed of light with respect to the train car plus the speed of the train car with respect to the ground. So once again, we would have the speed of light. This is, so of course, this is now going to be much longer, but allow us to just write it like this. And this is the speed of light with respect to the car. And this is our 100 meters per second. Of course, grossly exaggerated because we know this is much smaller than this, but bear with me. So according to this, the predicted speed of light with respect to the ground will be this much. This is our prediction. Except, once again, that when you do this experiment, you never get this. What you will observe is that this is the correct amount. This is the speed of light with respect to the ground, i.e. the speed of light with respect to the ground is no different than the speed of light with respect to the car. And it does not add up to the speed of the train car. So, once again, we have a problem with the old theory. Newtonian relativity does not give us the right result when we consider objects that move extremely fast. Okay. So here is how Einstein resolved these difficulties in the theory. So Einstein essentially says, okay, we're going to do the following. We're going to assume that the laws of physics remain valid in all inertial frames. We're not going to touch that. We're not going to say that the laws somehow are different when you transform from one frame to another. We're going to hold that to be true. Einstein is just postulating. He's just making a statement which essentially makes sense but does not have a basis in any experimental evidence. A postulate is a statement that you make boldly, and when your calculations turn out to be correct, then you can say that your postulates were indeed correct. So we now state the postulates of special relativity. There are only two of them. One is called the principle of relativity, which is very much like what we stated earlier. And you can say this in one of two ways. You could say that the laws of physics remain valid in all inertial frames of reference. And by this, we're trying to say that there is no special frame of reference. So there is no absolute. There is no absolute or preferred or special frame of reference. The second one is the constancy of the speed of light. And the constancy of the speed of light simply says the following. The speed of light in vacuum is 3.0010 to the 8 meters per second. And of course, here you can see that we're using the approximation because the speed of light is actually 2.99792.485, but bear with me. We shall use 310 to the 8 meters per second for all our discussions. So the speed of light is 310 to the 8 meters per second in vacuum in all inertial frames of reference. It does not depend on the speed of light of the light source or the speed of the observer. So the speed of light in vacuum is c, which is 3.0010 to the 8 meters per second in all inertial frames of reference. It does not depend on the motion of the source or the motion of the observer. So you would find, after we have gone through special relativity, that the calculations are not that difficult. What is difficult turns out to be the concepts. So the second postulate means the following. Look, if you're here, if you're just standing here, and your colleague is standing here, and they have a flashlight, and they turn on the flashlight, and so you see light coming towards you. This light, you will measure its speed to be c, 310 to the 8. If you're here, and this time your friend happens to be on a spaceship, and has a means of turning on a flashlight. Well, first of all, let's say that the spaceship is moving at a very high speed. Let's say 0.3 times the speed of light, about 1/3 of the speed of light, which is very fast. If they turn on the light, you will still measure the same 3×10⁸ meters per second. You will not measure a faster time because the spaceship is moving towards you. This is the postulate that describes the constancy of the speed of light. So then Einstein, after these postulates, went on to deduce consequences. What are the consequences of these postulates? And the discussion of special relativity is all about the consequences. And let's begin a discussion of the consequences. So consequences of the two postulates. The first of these is called the relativity of simultaneity. The relativity of simultaneity, which essentially says that it is possible for two observers to disagree on whether or not two events were simultaneous, whether the two events occurred simultaneously, depending on their relative motion. And let's demonstrate this. Once again, let's consider an observer sitting or standing in a train car and standing right here in the middle. Okay, let's call this point here A and this point here B. Let's say that on the embankment is another observer. This is A prime, this is B prime. This train is moving at some speed V, so it's going from here to there. But at the very instant when this train got to here, as I've described, lightning struck point A and point B. Now, the lightning struck point A and point B. Remember that this observer is equidistant from here to there. It's exactly between, and so similarly, this observer is also equidistant from here to there. Okay? What do they see? Do they agree that the light hit their eyes at the same time? Well, consider this observer here. When the light hits, then the light, you remember the wavefront travels as wavefronts to his eye, and the light travels as the wavefronts. Now, this distance is the same as this distance. So the two waves hit his eyes at the same time. So he says, the two events were simultaneous. But what about this guy? Don't forget this guy is in motion. So the light coming from point A arrives at this observer, because the observer is now probably somewhere here. Let's indicate that this observer has moved on somewhere here, so that the light from this lightning strike reaches their eye first before the light from point A. So they will say, oh, those two events were not simultaneous. One occurred before the other. This is the relativity of simultaneity. So, in words, two observers may disagree on whether two events occurred simultaneously. And this is true if they are in relative motion. Or if they're in two different inertial frames of reference. Okay, this is consequence number one. So Einstein then argues that, well, If we cannot agree that two times are simultaneous, then in fact it may well be possible that time intervals measured by these two observers may even be different. That's what we shall look at next. And you'll have to bear with me, there's a bit of algebra involved, so we'll do the algebra and then we can do problems in a subsequent lecture. So the second consequence is called time dilation. Once again, we perform a thought experiment. So here is a spaceship that is moving forward with some speed v. This spaceship has a diameter d and has a student sitting here who has a clock with which she can measure the time interval between events. The event that she is interested in, the two events are as follows. She has a flashlight here and she's going to turn on the flashlight so that the light goes up to the top where she has a mirror and the light bounces back down. And she's going to time the interval between send and receive. Well, she knows physics, so she simply writes, oh, the time interval is simply, well, the light traveled up and down, so that's 2 times d divided by the speed of light. For the purpose of what follows, we shall call this delta t O. Okay? Let's call this equation 1. Now let's do this from the point of view of somebody who is standing on Earth and is measuring the same 2 events, the time interval between the same 2 events. So they're going to see the following. The spaceship, do not forget, is in motion. And it's in motion at the speed v. When this person turns on the light, the spaceship is moving. So the person that's standing here, we shall call this the earth-bound, because they are on Earth looking inside the window in the spaceship. So they're going to see the light travel from here to here, back down here. So the light goes like this and like that. And I know that I have not drawn this quite well because I have put this too close. But the point is that the distance from here to there is the same as the distance from here to there. So this is L, and this here is L. And let's remember that our diameter, the diameter of the spaceship is D. So for this person, the light travels along this path here. And so he just completes the right angle. This is D. And so can write the following equation. So he writes that the time interval is the same as 2 times the hypotenuse divided by the speed of light. But at the same time, you can also write that delta t should be the same as the spaceship has moved a distance of 2L within this time interval. 2L over V. So if we can call this equation 2 and we can call this equation 3. Well, the algebra is as follows. we're going to try to express equation 2 and make use of equation 1. So from here we can write that delta t is 2, I'm going to take the d squared out of the parentheses, d squared, and I'm left with 1 plus L squared over d squared over the speed of light. And of course the square root of d squared, that's d, so that we get 2d over c times the square root of 1 plus L squared over d squared. But you recognize 2d over c as exactly what we obtain in equation 1. So delta t can be written as delta t naught times 1 plus L squared over d squared. We can call this equation 4. And in some ways we are done. Except that we have an equation that is dependent on a specific spaceship, the diameter of a specific spaceship. This equation is not general. So what we have to do now is to make sure that it's a general equation. And we can do that by taking equations 2 and 3 and doing a little bit of algebra. Well, let me continue here. So we can, since delta t is the same as delta t, we're going to set the right hand sides also equal to each other. And so we can write that 2L over V is the same as 2D squared plus L squared over C. We can cross out the 2's cancel out. We're going to square both sides to remove the square root sign, and so we get L squared over V squared is the same as D squared plus L squared over C squared. And I'm going to continue here. From here, we're going to cross multiply and write that V squared over C squared. So V squared over C squared is the same as L squared over D squared plus L squared. Remember that V, the speed of the spaceship, is less than the speed of light. So this here is the fraction. And in fact, we can subtract the fraction from 1 and I'll still obtain a positive number. So we do 1 minus V squared over C squared. And this gives us 1 minus L squared over D squared plus L squared. And let's use a little trick of algebra. We're going to write 1 as D squared plus L squared over D squared plus L squared. And from that we subtract L squared over D squared plus L squared. Which gives us, of course, the L squareds cancel. And then we can further divide through by, well, let's do this instead. So this gives us D squared over D squared plus L squared. And if we divide top and bottom by D squared, we end up with 1 over 1 plus L squared over D squared. We're almost done. We're almost done. Okay, now let's flip everything. Or better yet, before we flip everything, let's do the square root here. So we get, let's do the next line. So we do the square root 1 minus V squared over C squared is then 1 over the square root of 1 plus L squared over D squared. And then when we flip both sides, we get 1 over 1 minus V squared over C squared is the same as the square root of 1 plus L squared over D squared. And this guy here, this term here, notice that we have the same terms. So we end up by doing the following. So we have delta t is the same as delta t naught times 1 over the square root of 1 minus V squared over C squared. And we are done. we're done. This term here, 1 over the square root of 1 minus v squared over c squared, appears so many times in special relativity, and for that reason it's given a special symbol. We shall write it as gamma. We shall write it as gamma. So gamma is 1 minus v squared over c squared. Okay? And so we have our final result is that delta t is gamma times delta t naught. And since v is less than c, v squared over c squared is an even smaller fraction, so that the denominator here, so since we do 1 minus a fraction, so this here is a fraction. 1 over a fraction means that gamma is greater than 1, except for the special case when v is 0. So gamma is greater than 1, except when v is 0, which is a non-interesting case anyway. So given that gamma is greater than 1, clearly delta t is greater than delta t naught. This is time dilation. Delta t is greater than delta t naught. The time interval measured by the observer who sees the clock moving past them is expanded. The time intervals are expanded, dilated. So that's why we call this time dilation. The time delta t naught is the time measured between the two intervals by this person who was at rest when the two events occurred at her location. This time is called the proper time. So delta t naught is called proper time, or the proper time interval. Or the proper time interval. And delta t is the expanded or the dilated time and because we have run out of time, before I go though, we shall do a problem in the next lecture, but let's just, so that we do not leave any ambiguity, let's write out what these times stand for. So the proper time, this is the time that's measured by an observer who is at rest with respect to the two events. And the two events occurred at her location. Delta t, this is the time interval that's measured by let's make this measured by an observer for the case when the clock used to perform the measurement is moving. So it's the time measured by an observer for the case when the clock is in relative motion to the So obviously this second observer's measurement are done not at the same location because the clock and the two events moved past them. It was moving, so they will occur at different locations. But this is the difference between proper time and dilated time. And Einstein is clearly saying that the dilated time is greater than the proper time. Okay, and in the next lecture, we shall start from here and expand a little more on the idea of time dilation, and then we can do some problems before we consider another consequence of the two postulates. Thank you.